Welcome everybody to another episode where we ask what's up with the universe. Hey, I'm your host, Who, and I want to welcome everybody today who's joining me for the first time, or if you're actually joining me as a returning viewer, so welcome. If you're new, don't forget to hit that little subscribe button so you know exactly when I go live. If you like the stream, hit that thumbs up. If not, hit the thumbs down. I don't care. It's science. I just want to let you know that, first of all, I want to apologize if you see me being sporadic because I got an odd connection this morning. But we're going to go with this show because today we are talking about supernovas. Yes, supernovas. So, who has actually heard of a supernova? Well, the universe is a dangerous place. There's black holes, gamma ray bursts, pulsars. They can all cause serious damage or even destroy our planet if they were close enough. But the fact of the matter is that there is nothing in our vicinity that possesses an immediate threat, or at least for the next few billion years. The nearest star that could go supernova is Betelgeuse, or Betelgeuse, as however you want to pronounce it. It's about 640 light years away. In fact, this star could go supernova in a minute, in a year, in an hour. We don't know exactly. I mean, all astronomers know that it has reached its limits, and it could blow up at any second. And when it will appear as one of the brightest stars, other than the sun, in the night sky. But just how close will we have to be? Just how close will a star have to be to cause irreparable damage to Earth? Well, we're going to cover this today. So, what exactly is a supernova? Are they dangerous to Earth? How would the universe be different if supernovas never occurred? We're going to explore all these other questions, okay? About 100 years ago, we believed we lived in a place that was quiet and a safe little nice in the universe. Without a telescope placed above the Earth, protecting the atmosphere, we had little evidence of cosmic radiation. I mean, since the era of space telescopes, we know that the universe is filled with powerful radiations, such as GRBs, gamma ray bursts, X-rays, fast-moving atomic particles called cosmic rays. This radiation is not the kind of radiation we can detect with our normal eyes. So, where does it come from? One source is black holes in the center of the galaxies, because we have a supermassive black hole in the center of our galaxy. Another is the powerful magnetic fields around neutron stars. I mean, more commonly, radiation originates from a supernova, the powerful explosion marking the end of a massive star's life. One type of supernova, the ones we're mostly distinguishing here, is the explosion caused when a massive star dies and collapses. Like, only stars that contain about 8 to 10 times the mass of our own sun will go supernova. During this explosion, the star will blow off most of its mass. The remaining core will form a neutron star or a black hole. As you can see in this image right here, this is the Crab Nebula. It's a supernova remnant. It's a supernova remnant and not an actual supernova. This is called a Type 1a supernova, by the way. So, where does the radiation come from? Well, stars are powered by fusing lighter elements into heavy elements in the core of stars. Energy is then released from fusion reactions and material at extremely high temperatures in the form of gamma rays. Atomic particles, like atomic nuclei, are blasted away at high speeds from the shock wave of the supernova explosion. X-rays are generated once a shock wave formed the supernova explosion slams into the blown off outer layers of the star. So, what kind of stars will go supernova? Well, let's start talking about the lives of a butterfly. Let's use a butterfly as an example here, okay? A butterfly starts its life as a little egg. Then it becomes a caterpillar. And then a pupa, however you want to pronounce it. Then a full-grown butterfly happens. This grown butterfly lays eggs and some new butterflies are born. A butterfly's appearance changes at each stage in its life. Changes that cause it to look nothing like it did at an earlier stage. Stars also go through this stage in their life. Stages that cause a star to change its appearance as it progresses through each stage in its life cycle. Stars are different masses, progresses at different rates, and have different fates. So, let's walk through the life of a star. Our sun, and then the life of a hot massive star. See, sun's like of all sizes can be born as protostars from a cloud of glass and dust in our galaxy. A star-forming nebula. When the protostar compresses under the force of gravity and its core becomes hot enough, the star begins fusing hydrogen in its core. And we got sun-like stars. For many billions of years, a sun-like star remains stable. Red giant. After 7 billion years, the star actually uses up its hydrogen in its core and turns into a red giant. We got planetary nebulas. At this point, the star goes through its unsettled stages, where it's losing its atmosphere, what's called the planetary nebula, which forms around a star. I mean, the cycle here is shown, as you can see in this little presentation here. This represents the recycling of the elements created in the star back to its interstellar medium, back into the gas and dust between the stars and the galaxy to provide new materials to make new stars. We got the white dwarfs. Well, the remaining core of the star cools down and shrinks to a white dwarf. Of course, after billions of years, the white dwarf cools off so much that it no longer glows and becomes cold and dark. Planets don't form from the planetary nebula in spite of the name. The name itself is left over from a time when our astronomers did not know what these nebula actually were. They hypothesized that these were planets because many looked simply like disks in a small telescope. Okay, the stages of a massive, let's talk about the stages of a life of a massive star. Massive star. For about billions of years, a star more than 8 or 10 times the mass of our sun will remain stable, fusing hydrogen in its core. A red supergiant. After 7 million years, the star uses up its hydrogen and its core, and it turns into a red supergiant. The star itself continues to fuse atoms in its core and into heavier and heavier elements until the core starts filling up with iron. Well, because the fusion process stops at iron, the core itself collapses on its own weight, no longer held up by the heat generated during fusion. We got the supernovas. Supernova. It's an explosion shock wave, and the energy that is generated from the core collapses, starts moving outward, heating the surrounding areas of the star, and to quote Jerry Lee, boom! Most of the stars blast out into space in supernova explosion. The cycle here is shown to continue from the supernova back into the cloud of gas and dust. This here represents the recycling of heavy elements created in the star and during the supernova explosion back into the galaxy to provide material to make new stars and planets. Sorry, wrong one. The neutron star. Anything remains of the star after the explosion turns into a neutron star, or a black hole. If the remains of the star are more than 3 times the mass of the sun, it turns into a black hole. So a really massive star explodes as a supernova. So let's check this out here. Let's start with the core of a red supergiant, which is about to go supernova. Here we go diving into the outer atmosphere of the star, getting closer and closer to the core. Of course, when you see this orange ball pop out here, you reach the center of the star. Boom! There it is. Where the star continues to fuse atoms into heavier and heavier elements until the core starts filling up with iron. Because the fusion process stops at iron, the core collapses under its own weight, and then boom again! An explosive shock wave, and the energy generated from the core collapses more rapidly outward, and most of the stars blasted into space with a supernova explosion, along with large amounts of heavy radiation. So, let's look at some of the elements here. Let's look at some of the special effects of stellar explosions. The GRB, the gamma ray burst. So what exactly is a GRB? A gamma ray burst, it's basically a sharp burst of very high energy radiation radiating from space. It lasts less than a second to a few minutes at a time. Well, once a source of GRBs, maybe the explosion of a very massive star where most of the gamma radiation released in the explosion is focused into narrow beams, with one of the beams pointed in the direction of Earth. We have many different satellites to help detect this, because GRB is detected with, for instance, the Swift telescope. It detects GRBs approximately once a day, but they are brief, intense flashes of gamma radiation. I mean, they come from all directions in the sky. They last from a few milliseconds to a few hundreds of seconds. All this radiation coming out at us from space, it might seem dangerous, and if we're too close to it, it is dangerous. So, how close would you have to be to? How close would a supernova have to be, or the source of gamma radiation, or the source of GRB have to be in order to damage any life on Earth? Well, here on Earth, we know that radioactive, I can't even talk, radioactive sources, like uranium, they all emit gamma rays. If we were to get too close for too long, the exposure to radiation can be harmful to us. So, how far away do we need to be? Okay, here is an illustration of the Milky Way galaxy and the location of our solar system in it. Let's zoom in a little closer, just to find out how close a supernova explosion would have to be. I mean, in order for the radiation from that supernova explosion to endanger life on Earth, we have to be really close. Okay, we zoomed in close enough, okay? The supernova would have to occur within about 30 light years for us for any radiation to take effect on life on Earth. That 30 light year distance is represented by the little white circle there around the location of our system. The nearest star-like to go supernova is over 250 light years away. Okay, so we found out that gamma ray bursts are more powerful than supernovas. No. Let's zoom out again and see how close the gamma ray burst would be to harm us. There's a danger rain for the source of gamma ray burst. I mean, it would have to occur within 8,000 light years within our own galaxy, and that'll be quite close to us. See, our galaxy is about 100,000 light years across. The nearest detectable source of a GRB is over 1 billion light years away, far outside of our galaxy. So right now, there is no danger from GRBs. Of course, in any case, there's still some amounts of radiation coming from space all the time. I mean, how has life changed on Earth has been protected from this constant barrage of cosmic radiation? Well, strange as it may seem, Earth's atmosphere and magnetic field shield us from most of this high-energy radiation. The atoms in our atmosphere, they absorb gamma ray and X-ray radiation, protecting us from that kind of radiation. Earth's magnetic field itself, it deflects or captures a lot of the Earth's fast-moving particles. But this also prevents us from detecting radiation here on Earth's surface. So, how does NASA study this radiation? Well, NASA has a number of telescopes out in space above the atmosphere to detect the steady radiation. Here are some of them I'm going to talk about. The XMN Newton. It's a joint mission with Europe, and Suzuka, a joint mission with Japan. They are currently studying X-ray radiation. Swift and Glass, they are primarily gamma ray missions. If you want to know more about these telescopes, you can look on the description below, and I put some links in there so you can check them out. See, supernovas, they might seem dangerous, but if stars don't die in supernova explosions, if they just cooled off and collapse, the universe itself will be very different. The supernova explosion releases a lot of elements created in the star during its lifetime, and it also generates new, heavier elements, all in a matter of a few seconds, like the oxygen in the air we breathe, and the water we drink. Silicon, it's in all of our electronics. I mean, hold up your cell phone. Basically, hold up your cell phone. We would not have cell phones without supernovas. How about gold? Gold for jewelry, gold for future space missions. Iron for steel, for blood cells, and of course to help rebuild Earth itself. You know, supernovas, they may seem dangerous, but in a universe without supernovas, there wouldn't really be a universe or life. So look at this. Here, we showed Orion before. This is Orion here. There are some stars that people think, which will go supernova. I mean, it may look like a lot of stars go supernova, but we can only see the biggest and brightest of these stars out there. Over 85% of the stars in our galaxy are small stars, like our own sun. The biggest star is Canis Majoris. If we was to put Canis Majoris in our solar system, the edge of that star would reach all the way to Jupiter. Of course, the stars are so far away that we can only see the brightest ones in the telescope. The most massive stars, they sometimes will go supernova, sometimes they won't. It depends on the star itself. Of course, we can certainly appreciate how our lives tie to the process of the supernovas to the rest of the universe through a spectacular event called a supernova. So, let's go see some of the stars that go supernova. At the beginning here, we asked some questions like, what exactly is a supernova? How dangerous are they to Earth? Would the universe be different if there's any supernovas? Well, as I said before, you can actually learn some more information about the telescopes that NASA and the ESU and other agencies are using, such as the SWIFT, GRBs, the Gamma Ray Large Area Telescope, the GLASS, the XMN Newton. All that's in the info under the description. And, one person actually said this best about stars. We are all children of stars, just like Carl Sagan said.
The lives and deaths of the stars seem impossibly remote from human experience, and yet we're related in the most intimate way to their life cycles. The very matter that makes us up was generated long ago and far away in red giant stars. A blade of grass, as Walt Whitman said, is the journey work of the stars. The formation of the solar system may have been triggered by a nearby supernova explosion. After the sun turned on, its ultraviolet light poured into our atmosphere, its warmth generated lightning, and these energy sources sparked the origin of life. Plants harvest sunlight, converting solar into chemical energy. We and the other animals are parasites on the plants, so we are, all of us, solar-powered. The evolution of life is driven by mutations. They're caused partly by natural radioactivity and cosmic rays, but they are both generated in the spectacular deaths of massive stars thousands of light years distant. Think of the sun's heat on your upturned face on a cloudless summer's day. From 150 million kilometers away, we recognize its power. What would we feel on its seething, self-luminous surface or immersed in its heart of nuclear fire? And yet, the sun is an ordinary, even a mediocre star. Our ancestors worshiped the sun, and they were far from foolish. It makes good sense to revere the sun and the stars, because we are their children.